as you can see here, this is our setup for the study of gamma ray spectrum, and this here is the sodium iodide detector along with the photomultiplier tube and other accessories. And it is important to note that near the end of it we have the preamplifier also. So the preamplifier is attached with the detector setup in itself, and so this is how it looks, the detector in the real world. And you can see what are the cables going through it. So this is the output cable from the preamplifier, okay. And so the entire detector stuff is, entire process, physics process is happening over here, photomultiplier tube and all that stuff which I have just discussed to you right now. And then after that the signal goes to the preamplifier, and then the preamplifier output comes through this cable and it enters this main amplifier which is inside this box over here. Now the second cable here is the one for the preamplifier power. Preamplifier needs some power, and this is also given by this setup. So this gives the preamplifier, and also the detector setup, sodium iodide, for it to work we also need high voltage supply, and this supply is given by this unit as well. So here, so this is the input for the high voltage, this is the input for the preamplifier, and this is the output from the preamplifier. So three cables, and these are all BNC type cables, these two are BNC type cables, okay. So regarding this main setup, which is basically, this holds the linear amplifier along with the single channel analyzer. So it's a compact setup over here. Let me first look into the back of this setup. So here we have got this knob for turning on, this one turning on, and this is fuse, and this is the preamplifier power, this one, and this is the high voltage which gives, this cable gives the high voltage to the detector, and the output from the preamplifier enters here, and this enters from here and it goes to the linear amplifier, okay. So, and this is the main cable. So let me now turn on the device. So here, yeah, so let me turn it on. You see the red light, and let me look into the front. And so this is the height. So start counter, and we will say yes, okay. And you see automatically this has been set in a mode that it will keep on counting up to 30 seconds, okay. So you have to record all the data for 30 seconds here, okay. So now behind this detector setup, you can see we have summarized what are the various practicals or experiments in the lab you can do. Of course this is an advanced setup, being a gamma ray spectroscopy experiment. So we can study the gamma spectrum for these three sources which are in our lab, and we can perform the energy calibration of gamma ray spectrum. Also we can study the energy resolution as a function of gamma ray energy. Now we can further do another set of experiments, and which is we can determine the activity of the source, and also I will talk to you about the sum peak for Cobalt 60 source. These are the additional experiments. If someone wants to do, they can use it during their project work, okay, and we can add something extra to it as well, okay. Now that's for later. Now regarding this setup, which is a combined box containing combination of both the amplifier, this part, and the single channel analyzer, okay. Now before I proceed, let me tell you that the detector we are going to use here has an operating voltage of 600 volts. So let me set it. So this is the high voltage knob. So as you can see over here, high voltage knob. Yes, so now I am going to turn it 600 volts, right? So okay, 10 turns after this, so 100 volts, and so 200, 300, 400, 500, and then 600 volt. Okay, so detector operating voltage. So this 6 shows 600 volts, and if we give this, then this is 590 volts. Okay, now operating voltage of 600 volts. Now we lock it like this. So this set can give us up to 1000 volts. Next, you say, is the amplifier. Now we will set the gain of the amplifier to 2 volts. And why do we set it? I will talk it about in just a few moments. Okay, to 2 volts I have set. And also you see the window for the single channel analyzer I have set to 0.5 volts. Again, this will be discussed later, and this is the one which we will play. We will change this baseline voltage. Okay, when we put the source over here, then you will notice the counts keep on going over here. Say for example, we will take data from 0.2 volt, 30 seconds we will take the data, then next we will take the data at 0.4 volts, and so on and so forth. This is how we will do the experiment. Okay, this is the lead castle. This is the lead castle where we have put the various sources. Okay, and we have to put it, and this box contains the sources, and this is our 137 cesium source. As you can see, the source strength is also mentioned over here. It's quite a weak source, and so we have taken this source, which is a 137 cesium source, out of our source box, and we have put it close to the detector over here. And now we will start our counter. Well, you see, okay, so now here we have started it, and the baseline voltage I have set, as you can see, to 0.8 volts, and this here, these are the counts, and the data will be taken for 30 seconds. So this is how you do the practical, starting from 0.2 up to 10 volts. You have to scan in steps of 0.2 volt. Okay, you see, just as it has stopped at 30 seconds, it again restarted. You have to note the data just before it reaches the 30-second mark. Okay, so let us again do this. 16. Okay, so 125, right? So we will note in our copy that the data corresponding to the baseline voltage of 0.8 volts is 125 or 125 counts. And after that, even though it is keep on changing, I will now do the change over here. So now I am going to take the data at 1 volt, as you can see, 1 volt, right? Okay, now so again we have started. So this is the correct data for 1 volt. We will disregard those counting scenario where we have changed the knob, because that will be incorrect. Now this one will be correct. So let us see how much counts we get at 1.0 volts. 394. So you understand, this is how you do this gamma ray spectroscopy experiment, basic one. Okay, so let me give you some more explanation of the concepts that we have discussed in our class. Alright, now you see, so what do we expect? What do we expect? You see, what we expect is a plot of E gamma, and this is count. Right, now for the 137 cesium source which emits the predominantly 662 kV gamma ray, we will expect something like this. Right, okay. However, note that this we will not get because we do not know it. First we have to calibrate this axis, and how do we do that? We, instead of E gamma, we do this plot channel, or either channel or in terms of discriminator voltage. So as I have shown you just now, we will be doing this plot in steps of 0.2. So from 0.2, 0.4, so on and so forth, up to we will take the data 10, because this is the maximum limit. We can take the data here in this entire range of 0 to 10 volts. Right? Okay. So now, what do we expect from this 137 cesium source? For this 137 cesium source, we will be expecting this plot. And what is this? This is the full energy corresponding to this 662 kV gamma ray. As I have already discussed before, that there will be contributions from the events which deposit their full energy into the detector. Fine. And what about this part? This is the contribution due to incomplete energy deposition. Fine. So gamma spectrum. Now this is due to complete energy deposition, this is due to incomplete energy deposition. What do we want? Of course, we want the information from this part. And what we are going to do this? We are going further find the energy resolution. So, in the first part of the practical, you have to take this count, right, or discriminator voltage, and corresponding counts, you make a plot. So this is discriminator voltage, and then this is the count, say n, then find the error of this count, which will be root n, right? Since we are taking the data only once, so this will be just root n, and then make a plot. You get this part. Okay, what's the second part of the practical? Just for this 137 cesium source, the second part is, after doing this plot, you see, so we have something like that, right? Now, what we are going to do, we are interested in this part. Next part is, we are from this part, after doing this plot, we will mark this point and say this point, and do a sort of linear interpolation. After this interpolation, we will subtract the corresponding data points from here to the linear interpolated part here. We will do the subtraction, and by doing so, what we will observe is we will get a new plot. which corresponds to only the full energy peak. So this is just the full energy peak upper part. So you can think of it as an ice cream cone, and we have cut this part together over here, and now we are showing this part over here only. So this is just the information for the full energy peak. I am just showing the full energy peak over here. Next, you do this plot, right? And then from here you mark the points. You mark this. Suppose this is at 2000. Then at 1000, you find this gap, and that will be your energy resolution, delta E. So from this part of the practical, using just only one source, which is the 137 cesium source I am talking about, and 662 kV, and we will be able to find the energy resolution, delta E. So now, but our task is not over, right? Why? Because using just only one source, 137 cesium, our main part is the energy calibration. That means we want to convert this x-axis from discriminated voltage to the energy of the gamma ray. And for that, what are the various energy points do we have? The first one is the, let me rub this part, okay? Okay. So we want to do an energy calibration, that is conversion from discriminated voltage to E gamma in terms of kV. So how do we do that? The first data point that we have from 137 cesium source is the full energy peak of 662 kV. This gives me one data point. So if I take this plot, and I find that around, say, 6.2 volts of discriminated voltage, this 662 kV is there. No, this should not be like that. Make it, say, 4.8. Okay. So we find from the plot that at 4.8 volts we are getting the full energy peak, which corresponds to 662 kV. So we get a sort of our point, right? So this is the discriminated voltage. So we put here 4.8, and the corresponding energy we know from physics. This is in kV, this is in volts. It is 662 kV. Okay. The next is this part over here. This part. This corresponds to your counter edge. Okay. Now you can do the calculation. I have told you last day how to do the calculation, and from the calculation you can get an estimate. Say you get the value at around, say, 300 kV. Say, I am just telling you. You have to tell me after this class what you found out, right? What you find from your calculations. And this corresponding voltage you are getting here corresponds to, say, 3.6 volt. So you put it like this, 3.6. And it is 300 kV. Okay, so we get two data points. Where is the third data point? Can anyone tell me? Well, the thing is that if I put just before the detector, we have the detector, right? Here. Okay. Not here. Here, let me see. So our detector looks like this. The mount I have shown you. This is the detector mount, and I have put this was put on a table. I have put the source over here, right? Now suppose if I put the source on top of the detector and I put a heavy metal plate, say lead plate, I put it on top. Not that heavy that it will destroy the detector. No, not that heavy. Small, this much thin, this much diameter, this much. Okay, I put it on top. Then what will happen? We talked about last day. So we will observe the backscattering effect. It will be dominant. It will become very increased. The backscattering events will be very much high, because instead of going in so many places, there will be large probability of coming back, right? And as a result, what you will see around this peak, if we again take the data for 30 seconds, we will see that this part somewhat is increased. Everything will remain the same, but this part you will observe a peak, and this corresponds to the backscattered peak. And so you can also do the calculation from theory where you expect the backscattered peak, and if you get the corresponding value, say you get it at 2.3 volts, no, not 3, say 2.4 volts, not 3 because we are taking in even steps, but from interpolation you can get also. Now 2.4 volts, then you will put the 2.4 over here and your theoretical value of backscattering peak over here. See, so just using this 137 cesium source, you are able to get 3 data points, and from this you can do a sort of calibration. Right? Now if I use another source, better, we will get more data points, and then we will do the calibration. So when our practical is the study of gamma spectrum. So what did we study? We studied this spectrum, and then we independent from this entire part, take out the full energy peak separately, we studied it, we calculate the energy resolution. Okay, now after doing that, what we did? We did the energy calibration. That means just using this source, we are able to get 3 points, and as a result, we can convert our x-axis to this energy. And next part, this is the first part of the practical, doing the energy calibration. The second part is estimating the energy, full energy, peak energy. Now, for this 137 cesium source, we have got only 662 kV. So we can get only the energy resolution from this 662 kV. Right? Right. Now, if I put some other source over here, we will get the energy resolution from that as well, say 22 sodium or cobalt 60. But for the simplicity of our case, I am just talking here on the blackboard the case for 662 kV or 137 cesium. Now regarding, you remember when I was discussing the detectors, I told you that I set the linear amplifier part, I have set the gain to 2.0 volt. Why is it so? The answer is the following. Suppose I want to do the experiment using cobalt 60. Now cobalt 60 decays predominantly by 2 gamma rays, 1173 and 1332. The higher energy one is 1332 kV. So 1173 and 1332 kV. Now get rid of this. Now, so from the cobalt 60, we sort of expect the spectrum like this, or maybe not like this, like this. Now, which one will be high? It also depends on the efficiency of the detector. That part I will speak to you later on. Now, you see, the first thing to note that in our detector, we have got the inherent limitation in this setup that all data must be between 0 to 10 volts, right? So this peak of 1332, it must arrive at some point below 10 volts. Now suppose, how do you do that? You change the gain of the amplifier. Suppose I change the gain so that this happens at, say, suppose I change the gain so that the 1332 happens at 2.0, then the entire spectrum will be squeezed over here. Now, do you want that? Of course not. Why? Because you have got this 2 to 8 volt entire range, and this is free. So this is your basically wasting the part of the spectrum. This is not a good way to do spectroscopy. Now, if you increase the linear gain a large, very high, then what will happen? It could happen that the 1332, if we keep on increasing the gain, the 1332 will keep on shifting. Now if I put the gain in a very large value, then it might escape the 10 volt range. and you will not be able to see. So that is not the good way to observe. Do the experiment. So we will have to change the gain of the linear amplifier so that we get a 1332 feet in a standard phase. Say for example at 8 MVA, 8 volts. So this is the reason for setting the gain at 2 volts. I have set it. You can even do the practical yourself and check it. That by setting the gain at 2 volts, you can get 1332 around that. And as a result, 662 you will get around 3 to 4 volts. Also, so everything is okay. You get the desired full energy peak in your spectrum. You can observe it. Okay. Now, regarding the working of the single channel analyzer, we talked about how it works in the two beams. So in the spectrum, let us see how it works. So you see, again let me rub it. Now this is the spectrum for 662 kV gamma ray. Now it is very easy to understand. That's why I am always trying to discuss it. Okay. So this is the 662 kV gamma ray. Now how do I observe it? I am putting. Suppose I am doing the observation at 0.24. What I am doing is I am setting a window from 0.2 to say 0.4 volts. I am setting a window and I am taking all the data that is there at this point and I am putting it at 0.2. This is how I am doing. Next, I am changing the window. You see? So, this entire spectrum will be scanned by changing the window. This is the basic idea behind the single channel analyzer. We are taking the data singly at a time. So, singly at a time. So, this is the baseline voltage. That means this lower limit of the discriminator. We are just changing it. And the upper limit we have set at a fixed value from the lower limit at say 0.2 volt. Okay, and by doing so, we will be basically taking the data in terms of bins, energy bins. And if we use the multi-channel analyzer, what will happen is that everything will be taken instantaneously at the time. Now, what in this experiment, we are taking the data at each point for say 30 seconds. Okay. And in the multi-channel analyzer, if you take the data for 30 seconds, you will get very few answers. But if you let it take the data for say 1 hour, then only you will be able to observe all the spectrum. Okay? Fine. So, another thing I thought I might have missed out, we have talked about the various possible processes, right? Photoelectric, Compton scattering, pair production and all that stuff. So, let me just say, I'll give you another basic example. So this is the detector, this is the source. Suppose some gamma ray comes here. For standard, let us use this 662 kV. So this is the full energy peak, or this is the total value of the E gamma. So E gamma energy is 662 kV. Right. Now after entering the detector, it deposits say 462 kV and 200 kV is escapes. Okay, so what you will observe in the spectrum? In the spectrum, if after doing the energy calibration, of course, so kV, if this is around 662 kV, then at 462 around, you will observe just one point. And then again, if such an event happens, then you will observe second point. So 1 plus 1, 2. And this is how the spectrum is calculated. Now let me ask you one question, which is, suppose we have got a Compton scattering, right? And after of 662 kV, and the amount of energy deposited is say 660 kV, and only 2 kV gamma ray escapes. Tell me. Now that's your homework. Tell me, such an event, is it possible or not? You have to use the same old Compton scattering formula. So this is the homework for you. Okay?